Chapter 6, Trigonometry, Lesson 2, Inverse Trigonometric Functions. So let's start by looking at the graphs of the original trigonometric functions first of all. So here we have y equals sine x, y equals cos x, and y equals tan x, at the bottom of the page. Now, you will hopefully recall from your work on functions that to have an inverse, a function must be one-to-one. So only one-to-one functions have a true inverse. And just a reminder, what do we mean by one-to-one? That means for every input, there must only be one output, and for every output, there must only be one input. Now, the trigonometric functions are not one-to-one. They are many-to-one functions. So, if we are going to define a true inverse function for any of sine, cos or tan, we have to restrict the domain of the original function in order to make it become a one-to-one function across that restricted domain. And in a minute, we're going to have a look at these restricted domains. Now, before we take a look at these restricted domains, it's important to actually understand that these were chosen arbitrarily. It is possible to choose different sections of each trigonometric function and find a portion of the graph that is one-to-one, but these particular restricted domains were chosen because they're the closest to zero, so they're the simplest versions of restricted domains that we can choose. I'm going to give you these in degrees and radians, even though the graphs themselves have actually been drawn with a x-axis in radians rather than the degrees. So, for the sine function, the restricted domain in degrees is that the angle, x, or theta if you like, has got to be between negative 90 degrees and 90 degrees. Now, in radians, the equivalent would be that x is between minus pi by 2 and pi by 2. And you can't quite see that on the graph here. You can see a portion of it from here to here, but the other portion is on the negative x-axis. Now, for cosine in degrees, the restricted domain is that x is greater than or equal to 0, but less than or equal to 180 degrees. And in radians, we would say that x is greater than or equal to 0 radians, which of course is equivalent to 0 degrees, but less than or equal to pi radians. Now we can actually see that on the graph here. So if we go from 0 to pi, that means we're only including this portion of the trigonometric function. We cut everything else off. And you can see here we allow every possible y value between minus 1 and 1, and there is a set of x values that will generate those y values between 0 and pi. So that's how we can restrict the domain, because we're still allowing every single y value that exists for the cosine function, but we're taking away extra unnecessary x values because the x values that run between 0 and pi are enough to generate all the y values between minus 1 and 1. Let's have a look at the restricted domain for the tan function. We would say in degrees that x is between negative 90 degrees and 90 degrees, but not equal to either, because of course there are asymptotes at those values, negative 90 and 90. And the equivalent in radians, x is between pi by 2 and minus pi by 2 radians, but again, we're not allowing equality to either of those two values for which tan is undefined. Now, you can see a portion of this here, like that, but the other portion will be down here. And again, hopefully you can see that every y value can be achieved, and we're allowing enough x values to achieve every single one of those y values, and we're then just getting rid of extra x values here. And the same with sine. You can see just by tailing the graph down like that, we'll generate all the y values between -1 and 1, and we have enough x values to do this. So we do have a full range, but we've done this on a restricted domain. Let's have a look at this in a little bit more detail. Now, on the left-hand side of the screen, you should see the sine function, y equals sine x, which has been drawn for its restricted domain. So ignore anything that is generated after -π/2 or π/2. We're looking at this red portion here. Now have a look at it. Can you see that we get the full range of y values? Every y value between -1 and 1 is fully covered by this portion of the sine curve. And we have enough x values that will allow us to do this. All the x values between -π/2 and π/2 will generate any y value between -1 and 1. So we've got full coverage of all the y values, and we've restricted the domain to x values between -π/2 and π/2 to allow us to achieve this. Now, on the right-hand side of the screen, the red graph is again y equals sine x, but I've also drawn the line y equals x, because of course if we reflect y equals sine x in the line y equals x, we generate the inverse function, which you can see in blue. Remember, function and its inverse are mirror images of each other in the line y equals x. And now we've restricted the domain of y equals sine x to -π/2 to π/2, then we can generate a true inverse function by taking the reflection of just that portion of the sine curve. So let's take a look at this inverse function, which is the blue function that you can see. Now, there is a special name for this inverse function, and it's not sine to the -1, which you have perhaps seen as a way of inverting a sine function previously, particularly perhaps back in Key Stage 3 in Year 9 when you first learned about trigonometry. There is a formal name for the inverse sine function. You need to know what it is. It is y equals arc sine x, and the arc refers to the fact that we are taking an inverse. Now let's take a moment to have a look at some coordinates on the original function and the inverse function as well. So on y equals sine x, we have the coordinate π/2, 1. Can you see it there? And on the inverse function, this would of course be a reflection of this coordinate, so it will be the coordinate 1 π/2. And the same over here, on the original trigonometric function, we have -π/2 -1, and that's reflected to give us -1 π/2. And that gives you an idea of the domain and range of the inverse function, which of course will be mirror images of the domain and range of the original function. And you need to know this. Now, having done this very successfully with y equals sine x, we're going to do exactly the same with y equals cos x and then y equals tan x on their restricted domains. So first of all, please turn your attention to the graph on the left-hand side. It is the graph of y equals cos x, but we have restricted its domain from 0 to pi. So I'd like you to make sure that you ignore any y values from before 0 and after pi, which are just sneaking into the diagram there. And this here is the function with its restricted domain. Now again, have a look at the y-axis. Can you see that all the y values between 1 and -1 are being achieved? There is a portion of graph for every y value between -1 and 1. And you can see that we have a full set of x values which will generate every single y value between -1 and 1. We've just taken out all the unnecessary ones either side. So we've got a portion of the graph with a restricted domain from which every y value can be achieved. Now, on the right-hand side, we have another diagram. And again, the red graph is y equals cos x. The black dotted line is y equals x. And then the blue graph is a mirror image of y equals cos x. You may wish to trace this out yourself and have a go at drawing the reflection to create the inverse function. Now have a look at this inverse function, which is in blue on the right-hand diagram. This is the inverse of cosine, so we call it y equals arc cos x. And be careful, there are two c's in arc cos, not just one c. Again, the arc refers to the inverse function. So let's take a look at some coordinates again. So on the red graph, y equals cos x, we have a coordinate 0, 1. We have this coordinate, which is pi by 2, 0. And then here at the end, you can see this coordinate, pi and negative 1 as a y value. Now, all three of these are reflected. So 0, 1 is reflected on the blue curve to give you 1, 0. Now, just for context, remember pi by 2 here is about 1.5, so you can see it's further to the right than this coordinate 1, 0. So that does actually make sense. This coordinate pi by 2, 0 is reflected here. It becomes the y-intercept of the blue curve rather than the x-intercept of the red curve. So that becomes 0 pi by 2. Again, remember what I said, pi by 2 is about 1.5, and you can see that that's lower than 2 on the y-axis there. So again, that makes sense. Now the final coordinate, pi minus 1 at the end there, is reflected up here, and that becomes negative 1 pi. So again, this gives you an idea of the domain and range of the inverse function. So now on to the graph of y equals tan x. So on the left-hand side, you can see the graph of y equals tan x, which is drawn for the domain x lies between minus pi by 2 and pi by 2, but not equal to either of those two values. Now, it's important to remember that tan, unlike sine or cos, does not have limitations on its y values. So let's take a closer look at the domain and range of y equals tan x. Now, we're restricting the domain, remember, so that x lies between pi by 2 and minus pi by 2. But the range is y is any real number, because y can be anything. Look at the graphs. Now, again, we're restricted by the screenshot, but the graphs just carry on going steeper and steeper and steeper as the graph gets closer and closer, infinitesimally closer to this asymptote here, but never actually reaches or crosses it. And the same in the negative direction. There's an asymptote here at negative pi by 2, and the graph continues to descend like that, generating more and more negative y values, but it never reaches that asymptote. So any y value is feasible. So when we take a look at the function on the right-hand side again, here is y equals tan x, and here's the mirror line, y equals x. Look at the blue graph, which is a reflection of y equals tan x in the line y equals x. It's the inverse function, which we write as y equals arc tan x. Now, of course, the domain and range will swap over. So arc tan x has a domain which is x, can be any real number. But its range is such that y has got to be between pi by 2 and minus pi by 2. And you know this, you know that the domain and range switch over for the function and its inverse. Now what you can't see, because again the screenshot limits this, is that this graph here would carry on like that, and then the inverse function would also carry on like that, and the same in these directions here. This tan graph would carry on infinitely like that, and then this blue graph would carry on infinitely like that, getting closer and closer to the asymptote. So y equals tan x has two vertical asymptotes, which I've drawn in purple on the left-hand side, but y equals arc tan x has two horizontal asymptotes like that, at plus or minus pi by 2 on the y-axis. So the asymptotes almost get reflected as well. So we have some information here in the table, but I'm also going to add in some extra detail about the original trigonometric function so you can compare the domains and ranges. Let's start with y equals sine x in red. Remember, we restricted its domain so that x was between pi by 2 and minus pi by 2 in radians. So remember, that's a restricted domain. For sine, cos and tan x, and the range for y equals sine x is that y lies between 1 and minus 1, so we don't lose anything from the original range. Now have a look and you can see how the domain and the range simply swap over between the function and its inverse, just as you have seen previously, because they are reflections of each other in the line y equals x. Now, what about for y equals cos x? Well, the cos function, we restricted its domain so that x lies between 0 and pi, and its range is still y between minus 1 and 1, no change there. So have a look, and again you can see the swapping of the domain and the range. Now lastly, y equals tan x, we restricted its domain so that x was between pi by 2 and minus pi by 2, not equal to either. And of course, when we find its range, y can still be any real number. And again, we have the swapping of the domain and the range. Now, one thing it's worth just mentioning here is that y equals tan x has vertical asymptotes at x equals plus or minus pi by 2. Of course, there are others, but I'm just talking about the restricted domain here. And y equals arctan x has horizontal asymptotes at y equals plus or minus pi by 2. So important to know those facts there. So you should now have an understanding of the restricted domains for y equals sine x, cos x and tan x, why we restrict those domains, and that's because we force the functions to behave like one-to-one functions, and the domains are chosen to allow every y value to be achieved, but for minimal x values. So we take the minimum amount of x-axis that will generate the full set of y values. So we kind of minimise the graphs in each case by restricting the domains. When the functions become one-to-one because of the restricted domains, we can then identify the inverse functions for each of these trig functions. And the inverse functions are identified by the word arc. So arc sine x, arc cos x, arc tan x. And you've seen on the 3 previous slides the sketch diagrams of each of the inverse functions and the clear reflections of the original functions on their restricted domains in the line y equals x. Now lastly, you need to understand that the domains and ranges of functions and their inverses swap over. So if you know the domain and range of the original trig functions, you then know the domains and ranges of the inverse trig functions. I'm just going to end on a point of vocabulary and notation. You have all actually come across the inverse trigonometric functions back in year 9 when you first learnt about trigonometry. You learnt about sine minus 1, cos minus 1 and tan minus 1, which you use to calculate an angle or solve an equation like sine x equals 0.5. Now, these are essentially equivalent to arc sine, arc cos and arc tan, but use of formal notation like this allows us to avoid any confusion about what the -1 means, and it's really important that we understand that sine to the -1 does not mean 1 over sine x. 1 over sine x is of course the reciprocal trig function, which is cosec x, and so on and so forth for the other trigonometric functions. So please don't get confused between the two things. So at the end of this, you've got to remember that for y equals sine x, as an example, this will of course apply in a similar way to cos x and tan x. For y equals sine x, y equals arc sine x is the inverse function. And you can think of it as equivalent to sine minus 1x. And separately, y equals 1 over sine x is equal to cosec x is the reciprocal function. The inverse functions and the reciprocal functions are different things. They are not the same concept. So just as a quick final summary, you need to remember that reciprocal and inverse trig functions are two different concepts. So the reciprocal trigonometric functions, you will remember from the previous lesson, are 1 over sine x, which is equal to cosec x, 1 over cos x, which is equal to sec x, and 1 over tan x, which is equal to cot x. Now, these are different to the inverse functions, where we now know sine minus 1x is arc sine x, cos minus 1x is arc cos x, and tan minus 1x is arc tan x. But as I've been saying, we're going to use the more sophisticated notation, which avoids confusion, and we're going to refer to them as arc sine, arc cos, and arc tan x. It's not wrong to refer to sine to the minus 1, cos to the minus 1, or tan to the minus 1, but it is important that you understand the difference between reciprocals and inverses, and that you don't get confused between the two totally different concepts.